Hello, ladies and gentlemen. Welcome to our webinar in the occasion of launching our new product, Nanoindenter module in combination with atomic force microscope in scanning electron microscope. Together with our partner, Alemnis, we successfully cooperate for several years, and as a result, we created a 3-in-1 solution enabling easier and faster nanoindentation together with complex surface investigation. Today, we are happy to present the solution, and we would like to give you some ideas how this 3-in-1 concept works and what are the benefits of this correlation. I am Veronika Hegrova, application engineer at NenoVision company, and let me introduce Dr. Nicholas Randall, Vice President at Alemnis, who will be talking more specifically about technical advantages of nanoindentation with atomic force microscope. First, I will shortly introduce atomic force microscope in scanning electron microscope in general, and briefly mention the key benefits of nanoindenter with AFM-in-SEM. Then Nick will take over and get deeper into the technical advantages of such a combination. During the webinar, don't hesitate to ask questions. There is a Q&A chat window where you can write your questions, and our colleagues will be answering them right away. At the end of the webinar, there will be a short Q&A section where we will answer the most important questions loud to you. First, I would like to say a few words about the company NenoVision. It was founded in 2015 as a spin-off of Brno University of Technology and the Central European Institute of Technology. Brno is a city of universities, technology and science with a rich history of microscope development. That is why both Thermo Fisher and Tescan electron microscopes divisions are located here. In the same city, NenoVision started to design compact AFM LiteScope, which can be integrated into scanning electron microscope. This way, the true correlative sample analysis that combines AFM and SEM microscopy is achieved. Why we actually want to combine AFM and SEM systems? The motivation behind LiteScope design is that the AFM-in-SEM system allows for efficient yet complex in-situ sample characterization that combines capabilities of both techniques. For instance, you can measure exact 3-dimensional topography with magnetic properties combined with SEM fast 2D imaging and chemical analysis. The combination of these techniques brings you completely new possibilities for advanced correlative imaging, which allows you analyzing sample in a way that was difficult or even impossible by separate systems. Here you can see how we connect the microscopes. On the left, there is an SEM chamber. LiteScope body is on the SEM stage, connected through the feed-throughs to the controller. As NanoView and later Nanoindenter module is operated via web browser, if we connect to the same network as SEM computer, then we can operate SEM and AFM together from the same computer at the same time. In this part, I would like to quickly present few of the key advantages of using AFM in SEM. With LiteScope, we tackle the difficulties with complex sample analysis at nanoscale. We overcome the usual inability of in-situ sample analysis. And the third, we can precisely localize the region of interest. So this way, we are able to give scientists more time for analyzing the actual complex results by reducing the time spent by measuring the samples and with the double localization with separate devices. LiteScope is in SEM enables to investigate the sample complexly using unique method, the CPEM technology. I will be talking about the principles later in more detail. Here I would like to show you if we acquire simultaneously the data from different SEM and AFM channels, we get, for instance, here we have the secondary electron signals, and we can get mechanical properties, the topography, other SEM channels like EDX, etc., EBD, SD, and then we can correlate it in one three-dimensional image, each of the channels. The second important field is in-situ analysis. Since we integrate AFM inside the chamber, all the measurements are done at the same time, in the same place, and under the same conditions. For instance, thanks to no transfer between chambers, the sensitive samples are not contaminated by air. I'm happy to say that our ambassador for in-situ analysis is Mark Willinger from ETH Zurich, and I really like his claim that LiteScope is like Swiss Army knife inside your SEM. So simply the added AFM functionalities widen the possibilities inside the SEM chamber. I would like to enhance an extremely precise localization of the area of interest and tip navigation. Thanks to SEM resolution and the tip visibility, you are really able to navigate to the exact spot while saving a lot of time. LiteScope supports a wide range of measurement modes. We divide the techniques into 4 groups. So the first one are material mechanical properties. So we can measure the topography, the elastic properties by measuring energy dissipation, the nanoindentation, the spectroscopy modes such as force distance curves. Then we can measure electrical properties, so we can analyze the local surface potential, conductivity mapping, the magnetic properties by measuring the domain structure, magnetic domain structure, and the piezoelectric domain imaging. With these techniques, we have categorized a broad range of different applications in material science, such as one-dimensional and two-dimensional materials, steels and metal alloys, various nanostructures. Then also we have the semiconductor field like integrated circuits and solar cells. And last but not least is the life science. So, for example, we can measure the mechanical properties of proteins. As we were talking about different techniques and different applications, we didn't quite mention how the unique correlative probe and electron microscopy technology, shortly CPEM technology, actually works. So on the sample, the electron beam points very close to the AFM probe, AFM tip. During scanning, the AFM tip and the electron beam remain static, so sample is being scanned only by the LiteScope piezo scanner. This enables simultaneous detection and acquisition of AFM and SEM signals at the same time, in the same place and under the same conditions. This technology is unique to LiteScope and was developed for seamless data correlation. So as we can see, the captured AFM and SEM images are subsequently correlated into one three-dimensional CPEM view. CPEM view can contain multiple channels, as shown on the right of the slide, of tungsten chromium. For this particular application, the AFM topography was correlated with the signals from secondary electron and backscattered electron detectors. So actually the information from SEM was extended into third dimension using the AFM topography. And as you can see in the NanoView software, both SEM and AFM channels are being recorded during sample scanning at the same time. Of course, you can choose your combination of appropriate channels. Here you can see the AFM topography, secondary electrons, backscattered electrons, error, and local elasticity. As we now have discussed AFM in SEM, let's have first a quick look at the Nanoindenter module from Alemnis, what it is, and what great possibilities it gives us when measuring in combination with AFM and SEM. Nanoindenter module is designed by Alemnis. It is a well-known company in mechanical testing. Nanoindenter module enables quantitative analysis of local mechanical properties, such as hardness, Young modulus, etc. As we have both devices interconnected in situ in SEM chamber, it provides us excellent control over experiment. The fixed distances of indenter tip and the AFM tip allows us to quickly relocalize the measured spots and saves a lot of time. Further, this modular design ensures quick reconfiguration to the AFM SEM setup. Here is an image, how it actually looks in the SEM chamber. So we have the Nanoindenter module over here, the sample, and the probe holder for AFM tip. As we change to the SEM image in wide field, we can see both of the tips. So we have the Akiyama probe or another AFM probe and the Nanoindentation tip, here Berkovich. So with the fixed distance between the tip of AFM and Nanoindenter, we can move with an exact precision to the contact with both tips. Let's say a few words about the nanoindentation. In general, it gives you quantitative information about the material on micro and nanoscale. As the shape of the indenter tip is exactly defined, recording the pushing force, depth, the time, together with the known indented area, enables you to determine the toughness, fatigue, the stress of the material, etc. Anyway, there are some difficulties with real nanoindentation experiments. It is nice to know the minimal feasible indentation depth, which we can find by measuring the roughness of the indented surface before the indentation. Then, when we measure the pile-up effect, it can influence the hardness computation, because the contact area of the sample with the tip is changed. The third one is really time-consuming and actually challenging. If we have different devices, it's really hard to precisely navigate, especially when we need to repeatedly localize the indents. The solution overcoming these problems is the 3-in-1 Nanoindenter with AFM in SEM. So the optimized procedure is to localize the area of interest, measure the roughness by AFM, avoiding any cracks or impurities using the SEM observation. Then we make the nanoindentation tests, and using high-resolution AFM, we measure the indents for the real depth and pile-up effects, etc. How to actually install this solution into the SEM chamber? The procedure is quite easy. So first we dismount the SEM holder if there is any, and then we install the LiteScope inside the chamber. We fasten the screws to the SEM stage and connect the LiteScope via feed-throughs to the controller. Now we are ready to install the Nanoindentation module on top of the LiteScope. So first we move the LiteScope's head, so we have enough space, and insert probe and sample holder. There are a few little screws to fasten. First, we connect the cables of the Nanoindenter module via feed-through from the SEM chamber to the controller. Remove the tip cover. And install the Nanoindentation module head. We insert the sample into the sample holder. And finally, we insert the AFM probe. Now the installation is complete. So as you can see, the whole installation process is very easy. To give you an insight into the measurement and interconnections of these devices, I would like to shortly show you the operation during the measurement. We first get closer with the sample to the indentation tip. It's quite easy because you can see all the time in the SEM. We find the spot to be investigated, and then we slowly get into the contact. From the shadow effect, you can see that we are getting very close to the sample. As you can see, this little circle, here is the place where we would like to make the indent. The indent is done, and so we retract the sample and get away with the sample from the tip. As the SEM has the function for saving the positions, we save the positions of both tips. So now we got really easily into the AFM probe focus. And because it's the fixed position, we just move the sample in XY axis and then slowly in Z direction. Finally, we use auto approach function to get the AFM probe safely into the contact with the sample. As the AFM tip is now in contact with at the indented place, we can just measure the AFM topography of exactly same spot. So let's have a look at few examples of using this 3-in-1 solution. Here we investigated high-speed steel composed of 3 phases. As we can see, we found these 3 phases and did indents. Here is one of the indents, and we can see very nicely these phases in SEM contrast of backscattered electrons. Then, after the indentation of several areas, we measured the topography, so we can determine the depth, the pile-up effect, etc. And then we can measure, calculate from the curves the hardness, Young modulus, or other mechanical properties. There is another example of the transformation-induced plasticity steel. This is a very complex microstructure. Here I would like to show you that it's also possible to use another SEM accessories, not only secondary and backscattered electrons and AFM with nanoindentation, but you can also use chemical analysis as EDX, EBSD, etc. So because this functionality is not limited, so we can really get complex information about the sample surface. But to get deeper into what the Nanoindenter module can do and gives you what benefits, I would like to give a word to Nick, who will get really deeper into the indentation. So Nick, you can start sharing your screen.
Okay, thank you, Veronica. Let me just do that. Share. Okay. Can you see my screen? Okay.
Yes, I can see it. Nice.
Okay, good. Right, well, thank you, Veronica. I'm going to carry on now with the second part of this presentation, where I'm going to talk about the technical advantages of nanoindentation when it's combined with AFM, and also how do we evaluate the data and what can it give us. Okay, so here we can see a basic Alemnis system, and we can see an example of a typical nanoindentation. So you can see that when we're indenting, we're using an indenter of known geometry, and we're indenting the sample either under load control or under displacement control. Now the system works using an actuator here on the right where the indenter is placed, and the sample is mounted on an SEM stub here on the load cell. It's a little bit different when we optimize this system into the NenoVision LiteScope, which you'll see in a little while. Now, the resultant test, we basically generate a load displacement curve. And if we do that in the SEM, we can also see in situ what's going on. So, for example, in this case, we see a load depth curve, but it doesn't tell us what's happening at the material surface and what is the response of the material. Okay, and as you can see here, there are little striations on the loading curve, and it's only with in situ viewing that we see that we've got slip happening in the material. So the combination of SEM with nanoindentation is already very advantageous. And then when we bring AFM into the mix, we can learn a lot more about the sample surface itself. Okay, so let's talk first a bit about nanoindentation. Nanoindentation is basically a continued development from macro and micro indentation. The problem was when conventional indentation techniques were developed, the indentation depth couldn't be reduced too much because the indent could then no longer be seen in an optical microscope. So instrumented indentation or nanoindentation was developed where we monitor load and depth in real time. And this gives us a load depth curve, which is like a fingerprint of the material. So if you look at the 3 examples here, these are for different material categories. On the left, we've got elastic materials, so we can load up to a maximum and then unload, and there's basically no hysteresis between the two curves. This would be like low load indent into glass, for example, which is very elastic, or into a polymer. On the right, we have a typically plastic material. So this could be a soft metal like aluminium or gold. And here we see that the unloading curve is almost vertical. So there's very little relaxation of the material when we remove the deformation. Now, these are the two extremes. Most materials fall into a mixed category where there's some plasticity and there's some elasticity. And we call this an elastoplastic response, as you can see in this middle example here. Okay, so just to compare to conventional indentation, for those that are not familiar with nanoindentation, at the conventional scale, we make an indent with an indenter of known geometry, could be Vickers, could be Knoop, and then we need to measure the size of that indent under a microscope. With nanoindentation, the indent is so small, we can't do that because we can't see it. So we have to get our calculation of data from the load depth curve itself. Now, the way we do that is exactly the same theory as conventional indentation. So what is hardness? It's basically load divided by contact area, which is pressure. And we do this exactly the same way at the nanoscale. So from our curve, we know FM, which is the applied load, because we've set it in the software. And the contact area, AP, or the projected contact area in this theory, is taken directly from the calibration of our indenter shape. Typically, we might be using a three-sided pyramid, a Berkovich-shaped indenter, and so we know the area at every depth that it might be used at, and we use that calibration curve to understand what is AP at the contact depth that we're using. So simple equation will give us HIT, which is the hardness. IT shows that it's by instrumented indentation per the ISO 14577 standard. Now, in addition to hardness, we can also calculate the elastic modulus, as you can see here. So for this, we basically take the tangent of the unloading curve, and this gives us S, the contact stiffness, which is directly related to the reduced modulus E. Okay. Beta here is a factor accounting for the shape of the indenter that was used. And if we know the Poisson's ratio of the material, then we can also calculate the true elastic modulus. Now, nanoindentation is not just used for measuring hardness and modulus. It's a very varied technique that encompasses many different disciplines. You can see here some examples. So top left, we've got fracture toughness. So we're doing an indent here to cause cracking in the material. And from the crack lengths, we can calculate toughness or fracture toughness. Here we've got some pillar compression testing. So a lot of people are using nanoindentation in the SEM to do pillar compression tests. So this is a very interesting field because you can isolate a very small volume of material and understand how it deforms. Alemnis indenters work in both compression and in tension. So for tensile testing, we have a gripper kit that can pick up a fibbed tensile specimen and therefore do a tensile test at the small scale. We have a lateral force sensor to be able to do scratch testing. So scratch and abrasion of the surface, and also investigating how material recovers after scratching, which is very important in aesthetic applications. Down here on the bottom left, we've got lateral shear. So this is a more specialized application where we're picking up a fiber in a composite matrix, and we're basically displacing it tangentially so we can break the fiber out of its matrix and therefore measure the interfacial shear strength. So this would be a typical tribology type test. Then we've got bending and shear, so beam bending experiments using beams that are cut by focused iron beam. Cyclic indentation testing. So here we're looking at a 3D printed structure, very small, and we're actually doing a cyclic indentation test. The advantage of instrumented nanoindentation is you can program the indenter to do whatever you want. It can do a single cycle, a multi-cycle, a sinus mode cycle, a dynamic test, a pause, a creep test, a stress relaxation experiment. Highly programmable to do basically whatever you want it to. Final example here is mapping, and I'll talk a bit about this later on. This is the ability of the nanoindenter to map properties across the surface by making large arrays of indents. So this is an example across an interface, and you can see we're basically doing typically an indent per second. So very, very fast mapping, which then allows us to measure mechanical properties across the surface. Okay, so why do we want to combine AFM with nanoindentation? Veronica's already explained some of the advantages. Let me continue from that. So basically, the AFM allows you to image the surface with a very, very high resolution, much better than optical microscopy, and also in complement to the scanning electron microscope image. Now, the AFM also allows us to measure the roughness of the surface. It allows us to choose an area of the surface that is suitable for nanoindentation, and it can reveal phases that we wouldn't be able to see otherwise. Okay. It also allows us to image the imprint after indentation and therefore understand what is the exact material's response. Now, you can see here on the left image, we're looking at a grain in a microstructure. This grain is about 10 microns across, and this is the limit of optical microscopy. This is 1,000 times magnification. And the indents here are made with a 2 millinewton load, and they're basically dots on the surface. If we zoom in on this with AFM, you can see the image on the right, we start to see the pileup around these indents is actually very significant. And this is not something that we could see just from the load depth curve. So AFM imaging is crucial to understanding what's happening. Okay, also AFM can reveal material responses which otherwise we wouldn't see. So in the example here, this is a chromium oxide coating. The top curve and image show a low load indent. So this is up to 50 millinewtons. And you can see here that the indent looks pretty perfect. Now, if we go up to a much higher load, this is 200 millinewtons, we notice that there's a step on the loading curve. Now, if we don't have any imaging technique, we don't know what that's due to. It could be cracking, could be delamination, we don't know. And it's only by actually imaging the surface, as you see on the left here, that we see that we've got both cracking and the coating is completely delaminated from the substrate. So it's very important to be able to understand that. Here's another example. This is an indentation on a silicon wafer, a single cycle, and you can see the cracks emanating here out from the corners of the indentation. And if we do a multi-cycle on that material, you can see from the curve the multi-cycle is clearly defined, but we don't know how much cracking is actually happening. Here we see from the image that we've got both lateral cracking and subsurface cracking going on around the indentation site. Here's a couple more examples just to highlight the importance of being able to understand if there's pileup or sink-in around the indentation. Now, both these curves are made on two materials. One is a hard coating, titanium nitride on silicon, and the other is a soft polymer, polymethyl methacrylate, also on silicon. Now, we've gone through the indent into the substrate. That's why we see this step on the unloading curve. This is a phase transformation, pressure-induced phase transformation in the silicon. But what is interesting is that we see very nicely the pileup around the indent in the case of titanium nitride, but it's different to the case of a soft polymer where the material is simply pushed out to the sides. So AFM tells us exactly what's going on and what the response of the material is. Okay, finally on that note, the AFM can also be used to image the indenter. So we can see what the indenter apex actually looks like. And we can also image very shallow indents to understand if we have a tip defect. Now, with three-sided pyramids, the tip defect is not as pronounced, but with four-sided pyramids, such as the Vickers shape, at very low loads, it's almost impossible to have a perfect apex, and we usually have a flat in one direction, which you can see very clearly here in this AFM image. Now, if we want to investigate, for example, a coating, then we can make indents at various depths. So here we see a titanium coating on silicon. So we've made indents from 25 nanometers depth up to 1.2 microns, okay? And the coating thickness here is about 300 nanometers. So at the very shallow depths, we're only measuring the coating properties. As we go deeper, we start to have the influence of the substrate. And around 300 nanometers, we're actually into the substrate. And there we start to see pileup increasing proportionally as we go up in depth, okay? So obviously the depth of indentation is very important, especially in a coated system, to understand, are we really measuring the mechanical properties just of the coating or of the substrate, or is it a mix of the two? And AFM helps us to understand that. We can also see how good the AFM is at telling us the surface roughness. So for example, at very shallow depths, we can see that the indentation size is basically the same order of magnitude as the surface roughness. So therefore, we're not going to have a very good contact between our indenter and the material itself. Okay, now, one thing from these indents on coatings is to highlight how we can use AFM data combined with the nanoindentation data to calculate hardness in different ways. We're all familiar with calculating hardness using the Euler and Farr method, which is basically the accepted method now for getting data from the load depth curve. So from those indents that we just saw, we can plot H-calc. This is the hardness from the load depth curve, but that doesn't take into account any pileup or sink-in around the indentation. So there are other methods which can be used. Now, one of them, H-work here, this is the hardness calculated by dividing the plastic work of indentation, so the area AP here under the curve, by the residual plastic volume. Now, we get the residual plastic volume from defining the edges of our indent in the AFM image, and then by software, we can calculate the actual volume of this indent. And by dividing AP by the volume gives us H work, which we can see plotted here for those depths through the coating into the substrate. The third method is what we call HSFM, and this is the hardness calculated by dividing the maximum load of each indent by the projected contact area, but not measured from the curve, measured directly again from the AFM image. So we're basically measuring the area defined by this dotted line. And so this gives us a hardness calculation which takes into account the pileup around the material. And so very clearly here, if we plot those three methods on the same axes, this x-axis is the ratio of indentation depth to film thickness. So 1 is basically the interface between coating and substrate. Anything deeper than 1, we're into the substrate. And what we see that while we're in the coating, where we know there's not much pileup, the three methods are fairly similar. But as we go into the substrate and we start to get much more pileup, we see that the methods start to give different results. And that makes sense, because when we start to take into account the pileup, then we've got a larger area for the same load, and therefore we're underestimating the hardness, if we like, or getting a lower value, which is what we see here for HSFM, which is the bottom curve. So very interesting to understand what's going on at the interface. So as Veronica showed earlier, some examples on high-speed steel, being able to zoom in on specific grains within a microstructure and then imaging those with extremely high resolution AFM. This is a very interesting technique. And we can see a couple more examples here. Taking a cross-section through an indent also tells us more about the pileup in a quantitative manner. Now, just one point, the Alemnis system itself is modified for the LiteScope, but for someone that purchases a LiteScope with the nanoindentation module, they also have the option to upgrade that later to a full Alemnis Nanoindenter platform. The advantage of this is that you can use that platform also outside the SEM for ex situ operation, or you could use it in situ for doing other types of experiment. For example, controlling the environment, so doing high temperature nanoindentation, low temperature nanoindentation, or for doing experiments with extremely high strain rates, which is another growing field. So for that, you basically keep the displacement actuator and the load cell from your LiteScope nanoindenter setup, and you purchase the upgrade, which gives you a full frame, and there you can also change the load cells and get up to 2.5 newtons maximum load. So we have 3 different load cell possibilities, and also different maximum depth actuator possibilities. Okay, in terms of software, there are 2 software packages that come with the Alemnis Nanoindentation system. Amix on the left here, this is the data acquisition software. So this is how you program the system to make an indentation. And on the right, we've got AMDA, which is the data analysis software. So once you've made your indentation, you load it into AMDA, and there you can calculate the mechanical properties directly. The Alemnis system can also, apart from being combined with AFM here, we can also combine it with other techniques such as optical microscopy, micro-Raman. We often combine it with EBSD and also with digital image correlation, which allows us to get strain mapping of materials when we deform them. And we can also put it into a beamline or a synchrotron in order to do tomography experiments. Just something about environmental control. You can see up here the high temperature module mounted on our platform. So this allows you to get up to 1,000 degrees Celsius. We have a cryo module for getting down to about -150 degrees C. We have quite a few systems in nuclear radioactive chambers for looking at different levels of radioactivity in materials. And we also have a couple of ex situ environmental control solutions. One is the bioindenter, where the sample is placed in a humidity controlled cell. And we also have a liquid cell for doing fully submerged testing ex situ. So very varied environmental control depending on your application. And just to finish with, I wanted to come back to the fast mapping solution, because that's really the direction in which nanoindentation is going, to be able to map arrays of indents across a surface. And if you can combine that with AFM, it means you really have a powerful technique for understanding mechanical properties and surface properties across fairly large areas. So mapping today is done very fast, typically an indentation per second, as you can see here. And it allows us to map properties. Here's the same high-speed steel sample we saw earlier. So it's got 3 phases. The soft manganese sulfide grains here, the light gray carbides, and the ferrite matrix. The white dotted line shows the area where we've made an array of 10,000 indentations. And you can see those indents in lines across the surface here. One of the big advantages of the Alemnis system is it's displacement controlled, which means all the indents can be made to the same depth. Whereas if it was a load controlled machine, then if you hit a softer phase, your indents are going to be much deeper for the same load. So it's usually better to use displacement control for doing large maps. So if we look at that surface, here's the hardness map. So every pixel of this image is 1 nanoindentation. And so you can see the soft manganese sulfide grains in blue. That's the lower end of the hardness scale. The very hard carbides are in red, high at the top of the scale here. And green is sort of intermediate. This is the ferrite matrix around. So this allows us to map those mechanical properties with a very high degree of precision. So here's the hardness map in the middle, the elastic modulus map to the right. The data can also be shown as histograms. And as we know the point where we touch the sample, we can also plot a topography map in 3D to show the topography of the surface. Here's the other example. This is mapping properties across two materials. So this is actually a sample of the a viewing window in the ITER nuclear fusion project. So here we've got Inconel and aluminium coming together, and we're mapping across that interface to understand what the mechanical properties, how they're changing across this zone. And here's a final example. This is an indent map of 100,000 indents on a steel surface. And you can see here what the indents look like, and we can still see with the secondary electron image, we can see the grain structure of that material. And here we can see the backscatter image in addition to the secondary electrons. And here we can see the maps that are generated there. So this is the hardness map on the left, modulus on the right. So quite clearly we can see the grain structure. And here we've actually got a map made using the max load values of all of those indents. So it's even better clarity on all of this grain structure and the topography image on the right. So thank you very much for your attention. If you have any specific questions on nanoindentation, you can always email me. This is the address. And if not, you can ask questions directly now in the webinar. So thank you very much for listening, and we're now open to questions.
Thank you, Nicholas, for your very interesting presentation. I'm going to share my screen. So first of all, I would like to summarize what we were talking about today. So LiteScope is a compact and easy to use AFM in SEM, allowing many measurement modes. The Nanoindenter module enables us to quantitatively measure mechanical properties such as Young modulus, hardness, stress, relaxation, scratch tests, etc. And so this 3-in-1 solution widens the possibilities of complex sample characterization in SEM. And so we really have a precise, accurate, and efficient, and also versatile, as you can use both of the devices separately, together, on the air, in the vacuum. So now we got into the Q&A section. So we chose few of the questions which we think are important to say loud. The first question was how much roughness of sample is allowed? So the scanner range of LiteScope in the Nanoindenter configuration is 100 micrometers perpendicular to the surface. So the typical roughness values on the nanoindentation samples are usually many times lower.
Maybe I can add to that, Veronica.
Yeah.
Typically, when we're doing nanoindentation, the ISO standard says that the surface roughness should be less than 10% of the indentation depth. So say, for example, you want to indent to 100 nanometers depth. That means your average surface roughness should be 10 nanometers or less. So that's the usefulness of actually measuring roughness by AFM, because then we can decide how deep we go with the indentation.
The second question is, it seems to me that there is a great need for manipulation space for the device connection. What is the minimum chamber size for which the device is applicable? So LiteScope fits to the most of the common SEMs. So, but it's up to your exact type of the SEM. So you can write us to our webpage or to your exact type of your chamber. So, and we can check it. The third, what is the range of the nanoindentation forces? So while nanoindentation module is mounted in LiteScope, the recommended indentation force is up to 16 millinewtons. If it is standalone, Nick can answer the question.
Yes, if you upgrade to a full Alemnis system, you can then change the load cells. So you can have either a 500 millinewton max load, a 1.5 Newton, or a 2.5 Newton. So we actually cover a very wide range of loads. So with the LiteScope setup, you can get up to 16 millinewtons. And if you need a higher load, then the best thing is to upgrade to the full Alemnis system. So you got the best of both worlds.
And last question is, to measure biological samples, there is no need to code it. And what about the vacuum? Well, for the coating, the limitation of measuring biological samples is SEM. If you have an SEM where you can measure without the coating, then of course you can measure it without coating. For example, cryos SEM or ultra high vacuum helps you with that. And I would like to pass the word to Nicholas, as I think at the end in the chat window there is more questions if you think something should be said loud.
I don't see that chat window, Veronica. So unfortunately, my meeting chat only shows very little information. I don't know why.
Here is one more.
It's the live event Q&A. This is what we need, right?
Yes.
Okay, now I see it. Okay, there's a question from Navid. Why do we get a higher Young's modulus by nanoindentation than the ultrasonic or tensile testing? So one of the reasons for that is that you're measuring a much smaller volume of material when you do nanoindentation. So you may have surface effect. So let's take, for example, a piece of steel. If you've polished that piece of steel, then the near surface region is going to probably be harder, and it may have a higher modulus because you've polished that piece of steel, and so locally it's work hardened near the surface. That could be one explanation. There's also what we call the indentation size effect, which is the defect of the Berkovich indenter at very, very low depths can transform itself into an increased modulus when you calculate from the data. So there's various factors which mean that we typically get slightly higher values from nanoindentation. There's another question here. Please explain the depth limit of coating for determining hardness without pileup. So this really depends on the type of coating that you have. If you have a soft material on a hard substrate, then any depth of indentation is probably going to cause quite a lot of pileup. If you have the opposite, let's say a hard coating on a soft substrate, then you can probably go relatively much deeper into the coating without having the pileup effect. So this question is really application specific. It depends on the two materials, the coating and the substrate themselves, how thick the coating is. As a general guide, we try and keep the depth limit to about 10% of the coating thickness, but in many industrial applications, this is not possible. So we want our indentation depth to be deep enough to overcome surface roughness, but shallow enough not to have the effect of the substrate. So it's really a compromise depending on your particular material. Okay, thanks very much.
Okay. Thank you, Nicholas, for a very nice explanation. With this, I would like to visit you. I would like to invite you to visit our virtual conference booth, or the web pages of NenoVision and Alemnis. And I would like to thank you for your attention. If you have any more questions, don't hesitate to write us an email. And so thank you.
Thank you all.